We have already mentioned projectile motion as an application of the fundamental equation of dynamics in the deduction of laws of force. Now we use the law of force for gravity to derive the equations of motion for projectiles. If we study the motion of a point-like body with the mass m under the influence of the gravitational force F with respect to the ground as a frame of reference, we can consider the projectile launched from an arbitrary point P with the initial velocity v0, where the angle between the direction of the velocity and the horizontal direction is denoted by alpha. We can choose a reference point O on the surface of the ground to describe the instantaneous and initial positions of the body by the position vectors r and r0, respectively. The fundamental equation of dynamics for such a motion states that the mass m of the body times the second-order derivative of the position vector r with respect to the time t is equal to the gravitational force F, which is given by the mass m times the gravitational acceleration g. As a result, the equation of motion of the point mass m states that the second-order derivative of the position vector r with respect to the time t is equal to the gravitational acceleration g. Since the mass m is eliminated from this equation, we can conclude that the motion of the body is independent of its mass. In the discussion on freefall, we saw that the gravitational acceleration g can be assumed as a constant, if the motion is limited to a small region near Earth's surface. This approximation allows us to attach a Cartesian coordinate system to the reference point O such that the z-axis is oriented in the opposite direction to gravity. Then the position vector r is given by the coordinate functions x, y and z, and the initial position of the projectile has the coordinates x0, y0 and z0. Similarly, the Cartesian components of the initial velocity of the moving body are denoted by vx, vy and vz, and those of the gravitational acceleration g are 0, 0, minus the magnitude of g. As a result, the equations of motion of the point mass state that the second-order derivative of the x and y coordinates of its instantaneous position respect to the time t vanish, whereas the second-order derivative of the z-coordinate with respect to the time t is equal to minus the magnitude g. By integrating these differential equations, we obtain that the x-component of the velocity v of the moving body, that is the derivative of the x-coordinate with respect to the time t, is equal to a constant c1. Similarly, the y-component of the velocity v, that is the derivative of the y-coordinate with respect to the time t, is equal to a constant c2. The z-component of the velocity v, that is the derivative of the z-coordinate with respect to the time t, is equal to minus the gravitational acceleration g times the time t, plus a constant c3. Here the constants c1, c2 and c3 are arbitrary integration constants. If we integrate the Cartesian components of the velocity v, we obtain the coordinate functions describing the instantaneous position of the moving body. Then we can write that the x-coordinate of the projectile is equal to c1 times the time t, plus a constant b1. Its y-coordinate is given by c2 times t plus a constant b2. Finally, its z-coordinate is equal to minus 1 over 2 times g times t squared, plus c2 times t, plus a constant b3. Here the constants b1, b2 and b3 are also arbitrary integration constants. The coordinate functions x, y and z with the 6 arbitrary constants are the general solutions of the equations of motion. Therefore the general solutions provide all the possible motions of a body under the influence of gravity. When we solve the initial value problem for projectile motion, we substitute the initial data into the general solution to obtain a particular solution of the equations of motion. The initial value condition for the equations of motion specifies the initial position r0 at the point P and the initial velocity v0 of the point mass at the initial time of 0 second. Then the initial data are given by 6 constants. The initial coordinates x0, y0, and z0 for the initial position of the body, and the components v0x, v0y and v0z of its initial velocity. We saw that the general solution of the equation of motion states that the x-component of the instantaneous velocity of the projectile is equal to the integration constant c1, and its y-component is given by the integration constant c2. The z-component of the initial velocity is equal to minus g times t, plus c3. Similarly, the general solution of the equation of motion consists of the following coordinates describing the instantaneous position of the projectile. The x-coordinate of the point-like body is equal to c1 times t plus b1, its y-coordinate is given by c2 times t plus b2, and its z-coordinate is equal to minus 1 over 2 times g times t squared, plus c3 times t, plus b3. If we substitute the initial values specified in the condition into the general solution for the time t equal to 0 second, we can express the integration constants in the terms of the initial data. Then we see that the constants c1, c2 and c3 are equal to v0x, v0y and v0z, respectively. That is, these integration constants are the components of the initial velocity v0 of the point-like body. Similarly, the constants b1, b2 and b3 are equal to x0, y0 and z0, respectively. That is, these integration constants are the coordinates of the initial position of the point mass. Then the instantaneous position of the projectile is given by the following Cartesian coordinates as functions of time. Its x-coordinate is equal to the x-component of its initial velocity v0 times the time t, plus the x-coordinate of its initial position. Similarly, its y-coordinate is given by the y-component of its initial velocity v0 times the time t, plus the y-coordinate of its initial position. Its z-coordinate is equal to -1/2 times the magnitude of the gravitational acceleration g times the square of the time t, plus the z-component of its initial velocity v0 times the time t, plus the z-coordinate of its initial position. The instantaneous velocity of the projectile is given by the following Cartesian coordinates as functions of time. Its x and y components are equal to the x and y components of its initial velocity v0, whereas its z-component is given by minus the magnitude of the gravitational acceleration g times the time t, plus the z-component of its initial velocity v0. Finally, the Cartesian components of the acceleration of the projectile is simply 0, 0 and minus the magnitude of the gravitational acceleration g, respectively. Here the kinematic variables of the projectile are described by applying Cartesian coordinates. However, we can also give these vector functions in a coordinate-independent form, stating that the position vector r of the projectile is equal to minus the gravitational acceleration g times the square of the time t, plus its initial velocity v0 times the time t, plus its initial position r0. The velocity v of the projectile is minus the gravitational acceleration g times the time t, plus its initial velocity v0, whereas the acceleration a of the projectile is simply equal to minus the gravitational acceleration g. These are the general expressions for the kinematic variables of a projectile, where the initial position and velocity of the moving body are arbitrary vectors. In fact, they could be expressed in a different coordinate system as well, but the Cartesian coordinates adapted to the trajectory of the motion provide the most convenient description of the motion of the projectile. The best way to adapt such a coordinate system is the following. If we choose the point P of the launch as the reference point O, that is the origin of the Cartesian coordinate system, then the Cartesian components of the initial position vector are 0 vanish. Furthermore, if we orient the x and y axes of the coordinate system such that the trajectory of the projectile remains in the plane spanned by the x and z axes, then the y component of the initial velocity v0 vanishes, and its x and z components can be expressed in the terms of the angle alpha of the launch. That is, Vx is equal to the magnitude of v0 times cosine alpha, and Vz is given by the magnitude of v0 times sine alpha. As a result, the x-coordinate of the instantaneous position or the vertical position of the projectile in such a coordinate system is given by the magnitude of the initial velocity v0 times the cosine of the angle alpha of the launch times the time t. The z-coordinate of the instantaneous position or the height of the projectile is equal to the magnitude of the initial velocity v0 times the cosine of the angle alpha times the time t, minus 1/2 times the gravitational acceleration g times the square of the time t. In these equations the initial data are represented by the magnitude of the initial velocity and the angle of the launch, and these two parameters uniquely determine the motion of the projectile. If we express the time t from the first equation and substitute the result into the second one, we immediately see that the z-coordinate of the projectile is a quadratic function of its x-coordinate, that is the trajectory of the projectile is a parabola, as shown in the presentation of the projectile motion in kinematics. The solution of the equations of motion shows that the most general motion of a point mass under the influence of gravity is projectile motion, provided the force of the air resistance acting on the moving body is negligible. We can generalize this result as follows. If the acceleration a of a point mass m is produced by an arbitrary constant force F instead of the gravitational force, then the fundamental equation of dynamics states that the second-order derivative of the position vector r of the body with respect to a reference point O, or its acceleration a, is given by the force F acting on the body divided by the mass m of the body. Since both the force F and the mass m are constant, the acceleration of the body is also constant. As a result, we can treat the fundamental equation in the same way as in the case of the motion of a body with uniform acceleration, where the equations of motion are the following. The instantaneous position vector r of the moving point mass is equal to 1 over 2 times the acceleration a times the square of the time t, plus the initial velocity v0 times the time t, plus the initial position vector r0. The instantaneous velocity v of the moving point mass is given by the acceleration a times the time t, plus the initial velocity v0, where the acceleration a is constant. These equations also demonstrate that if the force F vanishes, that is the acceleration is zero, then we have the special case of the uniform rectilinear motion, where the equations of motion reduce to the equations stating that the position vector r of the body is equal to its initial velocity v0 times the time t, plus its initial position r0, and the velocity v of the body is simply the initial velocity v0 for the vanishing acceleration a.